Welcome back everyone for another SVSU Math and Physics Resource Center tutoring video. My name is Brendon, I'm going to be your tutor, and for this video we're going to go into part 4 of the power series. We're going to do another example to find the interval and radius of convergence of a power series. Hope you guys enjoy. Alright, so let's jump right into this example. So trying to find the interval and the radius of convergence, just like the last two examples that we did, we're going to run the ratio test on it. So for the ratio test, first thing I'm going to do is I'm going to identify my a of n term. So there's my a of n, and then I'm going to go ahead and write out my a of n plus 1 term. Okay, so my a of n plus 1 term is going to be 4x minus 12 in the numerator to the n plus 1 divided by, and it looks like we'll get a negative 3 to the 2 plus n plus 1. So I'm just going to rewrite that as n plus 3. And then in here we'll get a n plus 1 squared plus 1. Okay, so we want to just simplify this a step further. So this is going to be 4x minus 12 to the n plus 1 divided by, and then this is going to stay the same, negative 3 to the n plus 3. And then this one, what you're going to want to do is go ahead and FOIL this n plus 1 squared term out. And what you'll end up with is an n squared plus 2n plus 1 from this term, and then a plus 1 from the outside. So it's going to be plus 2. Okay, so now that we have our a of n term, let's go ahead and run the ratio test. So for the ratio test, it's going to end up being the limit as n approaches infinity of a of n plus 1 multiplied by 1 over a of n. Okay, so then let's go ahead and plug in all of our pieces. So this is the limit as n approaches infinity of the absolute value of a of n plus 1. So this is going to be our 4x minus 12 to the n plus 1 divided by, and then this is going to be a negative 3 to the n plus 3 multiplied by our n squared plus 2n plus 2. And then we're going to multiply by 1 over a of n. So this is going to be our negative 3 to the n plus 2. I'm just going to change the order of that addition so we can do that. Multiplied by n squared plus 1 divided by, and then this is going to be our numerator for our a of n. So this is going to be 4x minus 12 to the n, absolute value. Okay, so now we want to just be able to cancel out as much as we can. So this 4x squared minus 12 to the n, that's going to cancel with this exponent of n here, because we can just, using our exponent rules, we can just imagine this being a 4x minus 12 to the first power multiplied by 4x minus 12 to the n power. So then the n powers are going to cancel out. Same thing with the 3, the n power is going to cancel with the n power there, and this 2 is going to cancel with 3 to make this a 1 here. Okay, so then let's see what we have left. So we have the limit as n approaches infinity of, so we have a 4x minus 12 left in the numerator to the first power, and then we have an n squared plus 1 left in the numerator divided by, now let's see what do we have left in the denominator. This canceled out. We still have this term, and then we have a negative 3 to the first power. So this is going to be negative 3 times n squared plus 2n plus 2. Absolute value. Okay, and then so since this limit is in terms of x, what we can do is we can pull out the 4x minus 12 and we can pull out this negative 3. But when the negative 3 is inside the absolute value, so when we pull it out, and remember the 3 is in the denominator, so it's going to be a positive 1/3. So we'll have a 1/3 times the absolute value of 4x minus 12, and we still need the absolute value on the 4x minus 12, because if this x value changes, this expression inside of the absolute value can be negative, so we need to make sure it stays positive. Okay, so then we have the limit as n approaches infinity of whatever we have left inside here. So it's going to be n squared plus 1 divided by n squared plus 2n plus 2. Okay, So now we just need to evaluate this limit. And if you go through and, I'm not going to do all the steps here, but if you go through and multiply top and bottom by 1 over n squared, you're going to get this to just to be equal to 1. So then this is just going to equal 1 over 3 times the absolute value of 4x minus 12. Okay, and so from the ratio test, for this series to converge, we need this to be less than 1. So now we just need to go through and solve this inequality and find the values of x that make this true. Okay, and so the way that we're going to do that is let's go ahead and pull out a 4 here. So this is going to be 4 over 3, absolute value of x minus 3 less than 1. And then so now we can go ahead and multiply both sides of the inequality by 3 over 4. So on the left side it's going to cancel. We're going to be left with the absolute value of x minus 3 is less than, and then 1 times 3 over 4 is 3 over 4. Okay, and then so dealing with the absolute value inside of an inequality, we're just going to add the other side. So we have a negative 3 over 4 is less than x minus 3 is less than 3 over 4. Okay, and so actually I forgot to mention at this step here we can tell what our radius is based on, if you go back to the first video, we have our x minus absolute value of x minus a is less than r. So our radius of convergence is equal to 3 over 4. Okay, so now finding the interval of convergence, we just need to add 3 to both sides. So 3 is the same thing as 12 over 4 with a common denominator. So when I add 12 over 4 to both sides, what that's going to give me is a positive 9 over 4 is less than x is less than 12 plus 3, so that's going to give me 15 over 4. So here is our interval of convergence. Now there is, when we have an interval of convergence that has two distinct endpoints, what we need to do is we need to test those endpoints to see if our series converges or not at those specific endpoints. So we know that anywhere in between these 2 points it converges, but now we actually need to check to see when x is equal to 9 over 4, does the series converge, and when x is equal to 15 over 4, does the series converge. So that's going to be the next 2 steps we have to do here. So let me go ahead and scroll down, and then we can go ahead and test those. Okay, so the first one is going to be when x is equal to 9 over 4. Okay, so let's write out our series. We have n is equal to 0 to infinity. Let's see, our series is going to end up being, so initially we had a 4x minus 12 to the n. So when we plug in our 9 over 4, the 4 is going to cancel, and we're going to be left with a 9 minus 12 to the n. So that's going to be a negative 3 to the n. And then divided by our original piece, so that was a negative 3 to the n plus 2 multiplied by n squared plus 1. Okay, and so now we want to go ahead and simplify this. So summation is n is equal to 0 to infinity. We can cancel out this negative 3 to the n and the exponent of n there. So this is just going to be 1 over, and then negative 3 squared is going to be 9 times n squared plus 1. Okay, so now we need to go through and run one of our convergence tests on this, or one of the tests that we can use to determine whether the series converges. So first thing I typically do is I try the nth term test for divergence. So I just give it a quick glance, I look at it, and I see what happens as n approaches infinity. Well, my only n that I have is this n squared in the denominator, and so my denominator is going to go towards infinity, which means my expression is going to go towards 0, which means that my nth term test for divergence is inconclusive. Okay, so then the next thing I try to do is direct comparison. And so it looks like we might actually have a direct comparison. So what if I let b of n equal to 1 over n squared? Now we know that this is a p series with p is equal to 2, which is greater than 1, which tells us that it converges through the p-test. So if p is greater than 1, we know the series converges. So then what we can do is, if we look at our series, our a of n, I know that if I'm taking my 1 over n squared and then I'm adding 1 to the denominator, and then I'm also multiplying by 9 in the denominator, my denominator of my a of n is always going to be bigger than my denominator of my b of n, right? So if my denominator is bigger, that means my expression's smaller, right? So then that tells me that through the direct comparison test, I know that my a of n converges because my denominator is always bigger, and so that means my expression is always smaller. So I have a smaller series than my b of n if my b of n converges. Okay, so that tells us we need to go back up to our interval of conversion, and we need to add a less than or equal to sign on our interval, because we know that since this is the interval of convergence, we know that at this endpoint, it also converges. Okay, so now let's do the other endpoint. So when x is equal to 15 over 4. So let's go ahead and do the same thing. We're going to write out our series, n is equal to 0 to infinity. And so we had a 4x minus 12. 4 is going to cancel again, so it's going to be a 15 minus 12. So this is going to be a 3 to the power of n divided by a negative 3 to the n plus 2 times n squared plus 1. Okay, so now I would really like to cancel these 3 to the n's, but I can't yet because this is a negative 3 to the n and this is a positive 3 to the n. But one way I can change that is I can add a negative here and then multiply by a negative 1 to the n, right? And so the way that this works is if I were to combine these together, because they both have the same power, I would just be multiplying negative 3 by a negative 1, which would give me my positive 3 back. So then this way I can cancel this out with the exponent here. So now my new series is going to be n is equal to 0 to infinity of negative 1 to the n divided by, on the bottom I'm just left with a negative 3 squared, so that's going to be 9 n squared plus 1. Okay, so now we need to determine if this series converges. And so since I have this alternating term, I know I'm going to go ahead and jump right into the alternating series test. So my b of n is equal to 1 over 9 to the n squared plus 1. Okay, so for the alternating series test, I need to see if it decreases. So that will be the first thing we'll look at. And so as n gets bigger, I know that this is going to get, my denominator is going to get bigger because I have an n squared in the denominator, and then I'm adding 1 and multiplying by 9. But as n gets bigger, my denominator gets bigger, which means my expression gets smaller, so that means we definitely decrease. And so for convergence, the next thing we need to test is the limit as n approaches infinity of b of n. And we need to show that this is equal to 0. So this is going to be the limit as n approaches infinity of 1 over 9 times n squared plus 1. Okay, and so as n goes to infinity, we can go and plug in our infinity here. So my denominator is going to go to infinity, so this is equal to 1 over infinity, which is just equal to 0. So then we have our second criteria satisfied for convergence. So then that tells us that at the upper endpoint, this x is equal to 15 over 4, we are also including that because on our interval of convergence, because it also converges at the endpoint. So our total interval of convergence is going to be this piece here. So this is the kind of difference between the other two cases where we had a radius of 0 and a radius of infinity. When we have distinct endpoints, what we need to do is we need to go through and test those endpoints to see if the series still converges on those endpoints. Okay, hope you guys enjoyed the video.